Good evening, everybody, and welcome to another session of Organic Chemistry lecture. In today's session, we are going to finish up on the discussion on stereochemistry, which is from chapter 5 of your book. And for today's session, we are going to finish the discussion on stereochemistry with a treatment of resolution of racemic mixtures. We will discuss what that is all about. Also discuss optical activities. See my pen here. And finally, we shall discuss the relationship between stereochemistry and organic chemical reactions. Okay, of course, before we go into all of those discussions, we are going to do the quiz problem that you guys have just taken. Do you want us to go over those? No? So, how many people say we should do the problems? Okay. Okay, so you want us to go over the problems? Okay, so let us do the second part of it, okay? Nineteen, go ahead and read this question first. Yes.
Consider the following molecule. How many chirality centers does it have? Determine the absolute configuration for each chirality center. And then draw all the possible stereoisomers and indicate the relationship between them.
Okay, very good, and thank you. How many chirality centers do you have in this molecule?
Two.
Two, exactly. Where are they? Right here? This here? And this here. Okay, so everybody got that right. So you have two chirality centers. Okay, how about the absolute configuration? R for both. How many people agree? No. Should I take your? You don't agree? Okay, let us number this carbon here. Let us go ahead and number this. This is carbon number 1, carbon number 2, carbon number 3, and carbon number 4. Okay, so what I will do, I will write the Fischer projection structure involving only this carbon here, and that is this here. Hydrogen on my left, carboxyl on top, and below you have this group that is attached to hydroxyl. And okay, keep in mind at this point, what we want to do is focus only on this carbon here. Okay, so let us make our assignment. What is A? Priority A, okay. B? Which one? Okay. Exactly. The carboxyl group. And then C is this group here. This is C. And of course this is D. Hydrogen is D. So now we want to make our motion from A to B to C. Ignore group D. Where? Which one? Which one? So we make our motion from A to B to C. Okay, and that motion is what? Counterclockwise. So that was supposed to be S, but but we have to change it because this hydrogen here, the group of lowest priority, is coming at you, right? So therefore, this becomes R. So those people who said R, you are correct. R is correct. So yes. Well, I don't know what you did. I don't know. I do not want to discuss exactly what you did, but you come and see me after I give you back your quiz, and then we could discuss that. Okay, so this is R. So this is R, okay? Now we want to come back now. Erase this. And now we want to focus on this other chirality carbon, this here. This here. So now we say that carbon is there, hydrogen is on your right, hydroxy group on your left. And what is priority? Okay, no, not yet. And on top here is your CH attached to nitrogen and also attached to carboxyl. And then below this is your methyl. Okay, so let us go ahead and make our priority. What is the priority here? This oxygen, right? What is B? Okay, this group is B. And of course, this is C, and this is D. Now we make our motion from A to B to C, and we ignore group D. And what is that motion? Clockwise, so it should be R, right? But the group of lowest priority is coming at you, so we have to change it. Okay, very good. So it's actually S. So therefore, this is S. Okay? Yes.
I didn't know that you had to count that whole group. I just put the carbon in D.
Well, I don't want to discuss that. Why don't you come and see me in the office and then we discuss that?
Okay, so what if we say for item 22, C1 is R and C2 is S?
Okay, now, the next thing is determine the absolute configuration. Now we want to draw all of the possible stereoisomers. We want to draw all of the possible stereoisomers. Okay, we start with by the way, how many possible stereoisomers are here? 4, okay. And then what do we do when we draw the first one? The mirror image. Okay, so let us call this molecule A, and we call this B. Okay, what other structure do we have? Oh, I'm sorry. Sorry about that. Also, mirror image, hydrogen. Okay. So what do we need to do now? Do what? Switch the groups to the other side. Okay. So we switch the OH to this side. And then the mirror image of that. OH. Okay, so now let us call this C and this is D. Okay, is that all? Okay, so what are the relationships between all of this? A and B? Enantiomers? Okay, which other enantiomers? C and D? C and D enantiomers? Okay, about what other relationship do we have? A and C, A and D, B and C, and B and D are configurational diractylomers. These are configurational diractylomers. Just a minute. Okay, yes. I don't want to get into a discussion of what each individual did. Okay. Okay.
Next time we have a question like that, we want all of the molecules in relation to each other,
yes.
or just the molecule that you're looking at?
No. The question is, draw all the possible stereoisomers and indicate the relationship between them. That's the question. So, all of them. Yes.
Question. When we did this in a previous class, why did you tell us there were 4 optical physics? Yeah, you only did 2. So you didn't tell us that there were 4.
I don't know exactly what you are relating to at this point. Okay, let us move on. Okay, number 2. Deja Brown, go ahead and read this first. Okay. Using this formula here, thank you. Using the formula C9, H18, what I want you to do is to draw 2 enantiomers. I'm sure the answer for this could be varied. Each one of you could come out with all different types of enantiomers as long as you use this formula here. Okay, so let us, yes. I can say that again. But okay, by enantiomers we mean those stereoisomers that do not superimpose on their mirror image. Okay, so let us draw an example of two enantiomers here using this formula. I could do this. Okay, how many carbon do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then I could draw the mirror image of this. Okay, how many carbon do I have here? Oh, C9, 18. That is not correct. Okay, we could change that. Okay, that is a possible molecule. So let us draw the mirror image of that. Okay, that is how many carbons do we have there? 1, 2, 3, 4, 5, 6, 7, 8, 9. As long as you use the formula that we have given you, you could almost write anything that any set of enantiomers that you wish to write. Yes. Yes. This carbon here is a catalysis. This carbon here. Okay, but this molecule here, this is a mirror. This molecule here, let us say this molecule A and molecule B. Molecule A and B are mirror images of each other, and they will not superimpose. Therefore, they are enantiomers, and that's all we ask you to do. Okay. Yes. Yes. Part of it. Yes. Okay. So anyway, so this is an open-ended question here. So and therefore you could give all kind of answers to that.
So rings and skeleton structures or tissue projections?
Skeletal structure?
A ring, anything, other considered pictures?
No. I didn't say that. Okay, now let us now use the same formula here to draw two configurational direct stereomers. When we say configurational direct stereomer, what are we looking for? How many chirality centers? At least two. Okay, you got to have more than one chirality center whenever you are discussing configurational direct stereomer. So, okay. Using that same formula here, so I could have this CH3. I could do this. This is what I meant when I say you could use cyclic. So we need one more chirality center. I could therefore do this. So how many carbons have I used already? 1, 2, 3, 4, 5, 6, 7. So we have 2 more carbons to go. Okay, that is one possibility. And then what would be the configurational direct aroma look like? Strict, exactly. The configurational direct aroma to this molecule will be this here. Okay, so everybody should be able to do this. So this here compound, if we call it A and we call this B, A and B will be configurational direct aromas. Yes. So it doesn't matter. Okay. Okay. Now let us go to today's discussion. Now, so far, we have been discussing different types of stereoisomers. We have given you examples of meso molecules, enantiomers, diastereomers, configurational diastereomers. Now, the question is, how do we know that these molecules actually do exist? Okay, there are many ways in which we could actually measure and detect the occurrence of all of these different stereoisomers. We could use instrumental methods. We could also use chemical methods. Some of those we are going to be discussing not only in this chapter, but in subsequent chapters. But if you take a look at the slide in front of you, we could use an instrument called a polarimeter to detect the occurrence of enantiomers and mixtures of enantiomers. What is a polarimeter? What you have here, a polarimeter is a device that takes your regular light, the light that we have right here, in which all of the rays of the light are directed in different directions, multi-directional. If you take the light and you pass it through this polarimeter, what the polarimeter will do is to what we call polarize the light, so that the light that is diffused in all directions is now going to be only unidirectional. Now, if you take that polarimeter, the polarized light, what we call the polarized light, if you take the polarized light and you pass it through a sample that contains an enantiomer, what that sample will do is to change the direction of the polarized light in 2 possible directions. You could either change it, say for example, you start with polarized light, pass it through the sample, of an enantiomer, and then when it comes out, the direction of that polarized light is being shifted either to the right or it could be shifted to the left. The degree to which that polarized light is shifted is what we refer to is what we refer to as optical activity. In other words, specific rotation. We say that molecule has a specific rotation. And therefore, we say that molecule is also optically active. So the specific rotation for different enantiomers are different depending on the type of molecule. Now, if you, on the other hand, if you have a mixture in which that contains both of the enantiomers, keep in mind the enantiomers are mirror images of each other. What will happen? As one of the enantiomer moves the polarized light to one direction, the mirror image which is present, which is the enantiomer, will move it back to the other direction. So therefore, what you have, when you have a mixture of enantiomers, you have zero rotation. Okay, you have zero rotation. Okay, so therefore you say that sample is optically inactive. So whenever you have the mixture, will be optically inactive, because it will have a specific rotation. The net rotation will be zero. On the other hand, if you have a pure enantiomer, the pure enantiomer will have a specific rotation, and we'll say that pure enantiomer is optically active. Pure enantiomer it will be optically the pure enantiomer will be optically active. Indeed, based on the optical activity, based on the specific rotation of a sample, we could actually determine the percentage of each enantiomer that is present in that sample. This is an example here. If you take a look at this molecule here, this is we say this is S glyceraldehyde. The specific rotation of glyceraldehyde is minus 8.7. The minus sign simply shows that it is rotating the plane polarized light to the left. On the other hand, if you take a look at this molecule here, S-alanine, the specific rotation is plus 8.5, which is saying that it rotates the plane polarized light to the right. Now, I do want to let you know that there is no relationship between the specific rotation and absolute configuration. There is no relationship. For example, take a look at this here. This is S. The absolute configuration of this carbon here is S, and still you have a specific rotation of minus 8.7. Similarly, you have a specific rotation of absolute configuration of S in this molecule here. The specific rotation is plus 8.5. So there is no relationship between the specific rotation and the absolute configuration. Yes. Yes. The positive means that it is that molecule is rotating plane polarized light to the right, and then negative simply means that that molecule is rotating to the left. Okay. So therefore, supposing if we have an enantiomer, let us just say, use a number. An enantiomer has a specific rotation of 7.5. Negative 7.50. What do you think this specific rotation of the enantiomer will be? What would be the specific rotation of the enantiomer? The mirror image. What will it be? It will be exactly opposite. Okay? With the same magnitude. Yeah, exactly. So the mirror image, the non-superimposable mirror image, which is the enantiomer, will have the same specific rotation, but different direction. In other words, if one is +5, the other will be -5. Okay. Now, whenever, yes. The number? Or the number simply tells us the extent at which that enantiomer rotates the plane polarized light. Okay, remember I told you. Sorry. Look at here, this here. The degree to which that molecule enantiomer rotates the light to one direction, that is what that number tells you. In other words, it is it's rotating this far to the right or this far to the left. Okay. Huh? What is it? Relationship? Well, every enantiomer, yeah, very good question. Every enantiomer has distinct specific rotation. In other words, we could use specific rotation to identify a given molecule. We know most compounds what their specific rotation will be, so we can use that to identify them. However, you cannot predict. You cannot say this molecule, unless you know about it. You cannot say it will have this particular specific rotation. That is an experimental value. Okay? Now, yeah. To do what? Number, what is it related to? It relates to the degree to which the light is shifted, either to the right or to the left. Oh, no. No, if you have a pure enantiomer, the pure enantiomer will have a specific rotation, which is distinct for that particular enantiomer. But if you have a mixture, an equal amount of the enantiomer, there will be no net rotation. Okay. However, if you have a mixture that is not equal amount, there will be a net rotation, and the amount of that net rotation depends on the concentration of each enantiomer in the mixture. Okay. Anyway, so if you have if you have a sample that contains equal amount of enantiomers, that sample is referred to as a racemic mixture. Or sometimes referred to as racemate. Okay, so a racemate is equal mixture, is a sample that contains equal amount of the two enantiomers. So if I ask you, would you expect a racemate to be optically active or optically inactive? Optically inactive, because they contain equal amount of enantiomers. Supposing you have a sample that contains unequal amount of enantiomers, would you expect that sample to be optically active or optically inactive? Optically what? Okay, exactly, optically active. Because they do not cancel each other out. Okay, so if you have a mixture in which you do not have equal amount of the enantiomers in the mixture, that sample will be optically active. Okay. So therefore, we also say that all chiral molecules will be optically active. All chiral molecules are optically active. Now, in that regard, we do expect a chiral molecule to be optically active? Yes or no? Optically inactive. Okay. Now, would you expect a methyl molecule? Will you expect a methyl molecule to be optically active or optically inactive? Why? Because the mirror image is always present. Exactly. Methyl molecules are optically inactive. So therefore, we could use a polarimeter to actually detect the presence of enantiomers in a sample. And we could also use the polarimeter to detect whether an enantiomer is present as a mixture of enantiomers or as a pure enantiomer. Now, we could use this in some chemical reactions. So now let us now go to the impact or the effect of stereochemistry on chemical reactions. Stereochemistry and chemical reactions. I know some of the reactions I'm going to give you now, this reaction we are going to be dealing with much later, but for now I simply want to use this just to demonstrate the concept of stereochemistry in relation to chemical reactions. If we have this molecule here, what type of molecule is this? What class of compound is this? A ketone? Yes. Very good. A ketone? Very good. Okay, so what I want to show you here. Okay, think of a ketone. Think of this here. Okay, this is some alkyl group. Think of this here as oxygen, okay? Just for the sake of this discussion. Well, I'm holding oxygen here. And then you have a carbon-oxygen double bond, right? That's a ketone. If you look at this part of the molecule, because of the hybridization of this carbon here, okay? What kind of hybridization is this carbon here? sp2, very good. So this carbon is sp2, right? If we have some molecule that want to react with this carbonyl group, because of the fact that this part of the molecule is flat, is planar, right? The molecule could approach from here. It could also approach from here. There is no reason why that molecule could approach from either from the bottom any faster than from the top. You follow that? Okay. Now, in this particular reaction here, we have this compound, lithium aluminum hydride, followed by water. If you react this with a ketone, now what does the lithium aluminum hydride do? It is a source of what we call hydride, which is hydrogen anion. That is what lithium aluminum hydride will give you. So this here, this hydrogen could approach this carbonyl from here, from the top, or it could approach, yes. Oh, let me write it better. I'm sorry, it's Al, it's lithium aluminum hydride. Okay? Now, the hydride, keep in mind the lithium aluminum hydride, this is lithium aluminum. You are going to see a lot of this in the future. It is a source of hydride, which is this here. Okay? And that hydride could come either from the top to attack the carbonyl carbon, or come from the bottom to attack the carbonyl carbon. When it does that, the final product is you will get this product with the hydrogen. Let me make it red so that we know the hydrogen is coming. Okay. Okay. That is supposing it comes from the bottom. Now, what happens if it comes from the top? What do you think you're going to get? You will get a mirror image of this here. Okay? Okay. If the hydride attacks the carbonyl carbon from the top, you get one product, which is be an enantiomer. If it attacks from the bottom, then you get the mirror image of that enantiomer. So in this case, the mirror image will be here. Mirror image will be there. So how do we know this happens? Because when you use the polarimeter to characterize the product that you form in this reaction, when you use the oh, sorry about that. So when you use the polarimeter to detect to characterize this product here, what do you get? What do you think the optical activity will be? Optically inactive, because the two enantiomers are formed in equal amounts. Okay? Okay? So the product of this reaction will be optically inactive. Optically inactive product mixture because you are forming the two enantiomers. Okay, so you begin to see the consequence of stereochemistry. If on the other hand, say we want to isolate the pure enantiomer, Okay, this reaction has taken place. We have formed a mixture of enantiomers, which is what we call the racemate. Keep in mind, the equal amount of enantiomers, we call this racemate. Supposing we actually want to isolate one of these enantiomers, or both of them. We want to isolate the enantiomers. How will you do that? What can you do here? Okay. How would you isolate the enantiomer? Because now we have formed a mixture, which is a racemate. So that takes us to the next topic. You call resolution of racemate. Whenever you are able to isolate a mixture of enantiomers into pure enantiomers, then you say you are resolving those enantiomers. So we refer to this as resolution of racemate. In this particular instance, the particular example I will use here, it depends on this specific molecule that we have just formed. In this case, we made an alcohol. Okay, so if we start with this, keep in mind we started with this. And we have its mirror image in there. Those are the two enantiomers. What we do, we then react the two enantiomers with a pure enantiomer. In this case, let us say we take a pure enantiomer. I'm going to react with this here. For the sake of this discussion, let us see here what will be the absolute configuration of this carbon here. Anybody can tell us? That would be A, B, C, right? So we move A to B, so that would be R, okay? So this is R. Okay? What would be the absolute configuration of this here? Let us do that. This is A, B, C, and D. Okay, we move from A to B to C, and that would be what? That's R. Okay, good. In order to save ourselves some time, I will simply now have, so we have, this is R. That means this is S, right? Okay, in order to save ourselves some time, I will no longer write these two structures. Okay, so the product we are going to form, we form two products. We form a product in which this here, this molecule here, will react with this here. The type of reaction we don't need to get into right now. To react with this, and then it forms what we call an R product, because the stereochemistry here is R. And then the product you are going to form here, what will it be? RS, exactly. Okay, so this will be S and R. Okay, the R, of course, is coming from from here. So let us make that blue, and this also blue. Now, what is the stereochemical relationship between these two molecules? Anybody know? Would they be enantiomers? Would they be enantiomers? You think so? These two. This molecule here and this molecule. Keep in mind, the molecule we are forming, we are joining this here to this.
Oh, you're joining them together.
Yeah, they are joining together. That's why we have RR. And then we are joining this also to this. And that is why we get SR. What I'm doing here is just saving some time by not writing the complete structure. Okay. Exactly. This and this will be diastereomers. Okay. They will not be mirror images. So see what we've done here. We started with a mixture, a racemic mixture or racemate, in which you have two equal amount of enantiomers, right? And then you react with a chiral molecule. You react with a chiral molecule. And the enantiomer reacts with the chiral molecule to now form two different molecules. And the relationship between them is diastereomeric. In other words, this is a diastereomer of this and vice versa. Now the key to this is, at this point, it is easy to separate diastereomer than to separate enantiomers. Enantiomers are difficult to separate because the difference between them is simply that they are mirror images. So if you can convert an enantiomer by joining with another molecule, and then you form a diastereomer in which you also using the enantiomer of that same molecule to react to form another diastereomer, you could separate the diastereomer. So now, what we can do now, we could separate this. Okay. You could separate this. And then at this point, so now this, we now have, in your sample, you have S, R, and R, R. Now we separated them. So once you do that, we could now use another chemical reaction to simply now come in, take this, react this with some appropriate chemical reaction or chemical reagent, and now separate the R. I'm going to call it the R alcohol. I'll call it the R chloride, okay? From the R chloride. And the process that we're giving you here is what we call resolution. So at this point, what have we done? We find a way to resolve a mixture of enantiomers. And how do you do that? You simply convert the enantiomer to diastereomer, and then you then release the enantiomer after you separate the diastereomer. So this process here is referred to as resolution. So we could actually resolve and form pure enantiomers. And some of you are going to the pharmaceutical industry, biochemistry, you're going to find this process very, very useful. Because even though generally when you perform most chemical reactions, you may form a mixture of enantiomers, it is possible to isolate those enantiomers by using the process called resolution. So at this point, what I want to do, since we are at the end of this chapter, I want to quickly run through all of the slides for the chapter just for the record. And this for the existence of a molecule to be chiral is that molecule will not superimpose on its mirror image. That is the absolute requirement for a molecule to be chiral. Okay? That is the absolute requirement. Okay, examples of configurational direct stereomers. We are going to chapter 7.
Are you going to post the lecture from Tuesday?
Yes, I will do that.
Okay. The question was
Okay. You want to wait?
again.
Oh, you want to see me on Tuesday?
Okay, I'll see you on Tuesday.
Okay.
Do you have prison dogs?
Oh, yeah. Just a minute.
Are they over there?
Excuse me, I just want to know if you could find my progress report for my scholarship.
Just a minute.